Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the whole of unit 6, which is the rate and extent of chemical change. In this video I'm going to go through the whole topic, tangents, equilibrium, Le Chatelier's principle. So without further ado, let's get into today's video. It's really important first to understand why we are doing this topic of rates, and it's really important for industry to know how fast the reaction's going, because for them it's vital that they're making as much product in as little time. So for an industry, they're going to be wanting to make as much money as possible, so that's why this topic of rates is so important. And there's two ways that you can calculate the rate of reaction. It's how much product you're making in a certain amount of time, or how much reactant is being used up in a certain amount of time. So let's have a look at a couple of example questions calculating the average or mean rate of reaction. Here I've got the rate of reaction of 8 grams of product being made in 30 seconds, and it wants my answer in grams per second. So quite simply, all I do is 8 grams divided by 30 seconds. And that gives me an answer of 0.27 grams per second. The next one over here is looking for the rate of reaction, this time of making a gas as my product. It's got 20 centimeters cubed of product being made in 30 seconds, and it wants my answers in centimeters cubed per second. There's two different units you could have for a question like this. It might want it in decimeters cubed per second, so I'll show you how to do that one just after. So for the first bit, 20 centimeters cubed divided by 30 seconds gives me an answer of 0.67 centimeters cubed per second. If it wanted my answer in decimeters cubed per second, all I'd need to do is convert my 20 centimeters cubed into decimeters, and the way to do that is by dividing by 1,000, so it would be 0.02 decimeters cubed divided by 30 seconds, and this time it gives me an answer of 6.7 times 10 to the minus 4 decimeters cubed per second. This question over here is a little bit trickier because it's wanting my units in moles per second, and it doesn't give me the moles, it gives me the mass, just like in the first question. So you almost need two separate calculations in order to get your answer for this one. So remember from quantitative chemistry that the number of moles is equal to the mass divided by the RFM. So to do this, I'm going to do 8 grams divided by, and the RFM of carbon dioxide, carbon has a mass of 12, oxygen has a mass of 16. I've got 2 oxygens, so it's 44 grams per mole. That's the RFM. And if I do that calculation, I get 0.18. But I'm just going to, because it's quite a long answer on my calculator, it's recurring. What I'm going to do is keep that on my calculator screen because I'm going to use it in my next calculation. And that is calculating the rate, which is going to equal my number of moles, which is 0.18, divided by the seconds, which is 30 seconds, and that gives me an answer of 6.1 times 10 to the minus 3. And try it out on your calculators yourself, and you should get the same answer as what I did, and put the units that are given, moles per second. What we're going to focus on now is factors that can affect the rate of reaction, and looking at something called collision theory. And what collision theory is it's the theory that particles need to collide with enough energy and in the correct orientation in order to react. If they don't do this, then they'll simply just bounce off one another. What we're going to do now is look at three different ways that we can increase the number of collisions or the energy that my particles are colliding with to affect the rate of reaction. And the first one is increasing the concentration of one of my reactants. So here you can see I've got my pink particles reacting with my orange particles, and if I just go down here, I'll show you what happens when I increase the concentration. All my particles are moving around in there, remember, and if I add more of one of the particles, there is more chance of collisions happening, and this is going to increase my number of successful collisions and therefore increase the rate of reaction. So the first thing I can do is increase the concentration of one of the reactants. The next thing I can do is I can increase the temperature. All my particles, like I said before, are moving around in here. Just look, I'm showing with arrows, they're all moving around. And if they move with enough energy, when they collide, they will react. Now, what happens when I increase the temperature to these particles? Well, let's have a look, shall we? Well, when I increase the temperature, what's going to happen is each one of these particles is going to move faster. This is going to increase the chance that they're going to collide, and it's going to increase the energy of them collisions as well. A good word to use in the exam would be these particles have an increased kinetic energy. Therefore, they collide with more energy, and there are more collisions taking place due to the fact that they're going to collide more often, because look at their movement, they're moving a lot faster. The last thing I'm going to show you to do with collision theory is something that you may not have heard of too much about, and this thing that can increase the rate of reaction is by changing the surface area. And I'm going to show you what that does to the particles. So up here you can see that I've got particles that are quite large. Well, what I'd be doing if I was to increase the surface area is still keeping the same amount, but making them a lot smaller. This increases their surface area, and I'll show you what that means by just changing this diagram below to show you. Now, as you can see, when I broke these particles down into smaller chunks, there's going to be a greater chance of having successful collisions because there's a larger surface the reaction can take place on. Something else important to mention at this stage is something called activation energy. And activation energy is the minimum energy in order to get a reaction started. And the reason why I'm talking about activation energy now is because it ties really well into collision theory and understanding it. So we've looked at the theory of how to measure the rate of reaction, but what does that look like in practice, and how can we relate this to practicals? Well, here I've got three different methods that you can use in order to work out the rate of reaction. Now, it's important to note that these three methods only work if you are making a gaseous product. And all of these require a stop clock in order for you to be able to calculate the rate, maybe measure the volume of gas in a certain amount of time, or measure the mass lost in a certain amount of time. So let's have a look at some of this equipment then. So down here, I've got a conical flask, and I have a delivery tube which is leading to what is called a gas syringe. This is one of the most common methods of measuring the volume of gas, and it's a very accurate way of measuring. If you look to the right, you can see there's an inverted measuring cylinder. That's a little bit less accurate than a gas syringe. I prefer using a gas syringe. They're easier to use as well. One thing you might have to look out for in an exam question, I've seen this before, is they've looked at mistakes that you can do with gas syringes, and you need to make sure that the delivery tube is not inside the liquid. If it is, it will not be collecting the gas, it will just be submerged in the liquid. So that's just one thing to look out for. Over here, I've got an inverted measuring cylinder. So what you need to do is fill up your measuring cylinder with water and place it inside a water bath. and what you do is measure the volume of gas by using this delivery tube again, and the bubbles are going to make the water level go down inside your measuring cylinder. Both these two methods involve measuring a volume of gas. We're going to look at a bit of a different method here, which can be used to give the mass of a gaseous product, or you could say the amount of reactant used by looking at how the mass goes down as well. And what I've got here is I just have an electronic balance. I have my conical flask with my reactants inside, and what you can notice here is I have cotton wool on top of my conical flask, and you might be saying, well, why do you have this cotton wool? Well, this cotton wool is really important because if you don't have it, you're going to get some evaporation taking place from the surface of your liquid, and the cotton wool is going to prevent this evaporation from taking place, and therefore you're going to have more accurate results. Now, with all three of these, you have potential systematic errors, like zero errors on your measuring equipment. This is when you start your practical off and it's not reading zero. For example, your gas syringe, when you push it down, it might not be reading zero exactly, it might be on 2, and this would have to be accounted for in your results. Same with the balance. The balance might be a few off, and this would affect your results as well. So it's really important to think about some of the errors that you could have with each practical that you look at. There is one other way of measuring the rate of reaction, which is by using a disappearing cross. If you've got a reaction which is making a precipitate, such as with sodium thiosulfate and hydrochloric acid, it makes sulfur solid. And this is an insoluble substance, meaning it doesn't dissolve in water, and therefore it comes out of your reaction as a precipitate. Now we're just going to have a look at what you could do in order to calculate the rate of reaction in this practical, and then look at what we could do with the results. So in this practical, what you could have as your independent variable is temperature. Now, it doesn't have to be temperature. You could affect how the concentration of hydrochloric acid affects your rate of reaction. But here we're looking at our independent variable as temperature. This means that my control variable will have to be the concentration of each of my sodium thiosulfate and my hydrochloric acid, and I'm going to need to keep the volume of each of them added as well the same. If I was changing the concentration of sodium thiosulfate, then my control variables would be temperature and volume as well. So in this practical, what you're trying to see is how long it takes for the cross to disappear. Now this leads to a few random errors, because if you have really good eyesight, maybe you can see it disappearing earlier. Maybe you are poor eyesight, so that's going to affect your results. So it's really important that you have the same person taking the results every time to account for this. But if you are doing this practical, you are going to get a lot of random errors because there's almost no clear endpoint for this practical. You also have, of course, got the standard random errors, which could be starting the top stop clock too early or too late. These are just random errors that you can get in any kind of practical, which leads to outliers in your results. Now, to get rid of random errors, the way to do this is by taking as many results as possible and identifying your outliers and calculating mean results for each practical. Now, what we're going to have a look at now is something called rates graphs, which you've taken your results for a practical and you now want to work out the rate of reaction. Well, we can actually do that by plotting ourselves a rate graph. So you're going to use your stop clock and you're going to time the volume of gas given off in a certain amount of time. Imagine you're doing one of them first 3 practicals we looked at, and what you'll notice is the shape of a rate graph always looks the same. The rate of reaction at the start is quite fast. However, over time, it slows down, and we'll talk about why that is now. So you'll end up with this curved graph shape, and you can plot your points and then use a pencil in order to draw a smooth curve for your results. So why do reactions always slow down? Well, if you just look at any normal reaction where you've got your reactants and you're making your products, well, what happens is those reactants get used up. And if you look over here, when the reaction's stopped, you're making no more gas. Well, what's happened is you have no reactant left. You only have product. And this really explains the curve of this graph. At the start of the reaction, you have lots of reactant present, and the reaction is going to take place very quickly. And at the end of the reaction, all you've got left is product, and it's going to go slower, or it's going to be stopped. As you can see by here, where it starts to go flat, the reaction is actually stopped. Let's have a look at what might happen, say, if you change the temperature or the concentration. Let's have a look at what would happen if I increase the temperature of my reacting solution. Well, this time what I would get is a much steeper graph. This is because the rate of reaction is faster. Just remember your collision theory. There's collisions happening more frequently with more energy, and I can use my pencil to draw a smooth curve as well. And look at that, the reaction still produces the same volume of gas because I've only changed the temperature. I've not changed the amount of reactant that I've had, but I'm getting a steeper gradient because of the fact that my particles are reacting with more energy and I have more frequent collisions. Now, how would I use a graph like this in order to calculate the rate of reaction? Because that is what's important about these rate graphs, isn't it? That we calculate the rate of reaction. And the real important bit to take frequent volumes at a certain amount of times is going to be important here in order to calculate the rate at a certain amount of time as well. So if we first look at calculating the mean rate of reaction, what you need to do is look at when the reaction stopped. So over here, the reaction has stopped here where it's flattened out, whereas over here with my higher temperature, my reaction has actually stopped here. So if I was trying to calculate the mean rate of reaction, what I would do is the amount of product, the volume of gas, divided by the time. I've just put a couple of numbers on my axis just to kind of show if I was making 60 centimeters cubed of gas in 40 seconds, I would do 60 divided by 40 to get the mean rate of reaction at 50 degrees C. For my 20 degrees C reaction, I would do 60 divided by 80, and that would give me the mean rate of reaction at 20 degrees C. But what is really cool about these rate graphs is that I can use them to find the rate of reaction at any time. Because as I said at the start, look at the reaction, it's slowing down. So if I want to calculate the rate at a certain amount of time, then I have to use something else. I have to use what's called a tangent in order to find my rate of reaction. So let's just pick a random time. Let's pick like 10 seconds. If I wanted to find the rate of reaction at 10 seconds at 50 degrees and 20 degrees, I could do that by drawing a tangent to my graph. And what you do is you put your ruler on your line and you want to touch it for as long as possible. And what you want to do is draw a straight line, and then you're going to calculate the gradient of that tangent in order to find the rate at that point. Now I've drawn my tangent, I can work out the rate by turning this into a triangle. So let's look at how that looks and then look at how I could work out the rate of reaction at that 10 seconds. So I've turned that one into a triangle, and if I turn this one into a triangle, you can see that this triangle here, it's much steeper, the gradient on this one, so there's going to be a faster rate of reaction, because what you're going to do is you're going to, just like you do in maths, to calculate the gradient of line at a certain point, you're going to look at the change in y divided by the change in x. So in order to work out the instantaneous rate, the rate at a certain point, what you do is dy divided by dx. It's a very common exam question in order to get an instantaneous rate, and it's often worth quite a few marks. Now, even if you can't work out the gradient of a line, it's you can still get some marks by just drawing that tangent. So even if you really struggle at calculating a gradient of a curved line, please do at least just draw your tangent. If you can do the next step, find out the change in y or the change in x, you will get yourself some marks on this question. We're now going to have a look at increasing the rate of reaction using something other than collision theory, and we're going to look at using catalysts. And catalysts work by lowering the activation energy, and they do this by offering an alternative route for the reaction. If we just have a look at a reaction profile for a exothermic reaction, remember from the topic of energy changes, we looked at reaction profiles. If we look at an endothermic reaction, if we look at an exothermic reaction, the products have less energy than the reactants, and that big hump is the activation energy. And what we do when we add a catalyst to the reaction is we are lowering the activation energy. So the reaction profile just looks like this. And catalysts have some great advantage in industries. They don't get used up in the reaction. So this means that they can last a long time. Also, they can lower the temperature and pressure that the reaction happens at to make it cheaper and more energy efficient. But they do have a couple of disadvantages. One of them being the fact that they are often rare and precious metals. Gold is a very good catalyst, and you obviously know that gold is quite an expensive material. And as well as this, sometimes they can create toxic byproducts. So when you're picking a catalyst for a reaction, they are specific to the reaction, and you've got to weigh up the advantages and disadvantages. Also remember that inside our bodies, we have catalysts in order to speed up our reactions, and they're called enzymes, biological catalysts. We're now going to have a look at a specific type of reaction called a reversible reaction. And a reversible reaction can be shown with this double-headed arrow. And the special thing about reversible reactions is that as well as the reactants making the products can react also to remake the reactant. Let's have a look at this specific reversible reaction, and here I only have one reactant. You can have multiple in a reversible reaction, but here I just have ammonium chloride. And when you heat up ammonium chloride, it makes hydrochloric acid and ammonia gas. So in here I have my ammonia, my NH3, and also my hydrochloric gases. And what's happening is I'm making an atmosphere, and I've got cotton wool on top of my boiling tube. And the reason why I have cotton wool is so that my ammonia and hydrochloric acid cannot escape. And because they cannot escape, what actually happens is they go back and reform ammonium chloride when it starts to cool down. And you can actually see it forming on the cotton wool up here. I have that ammonium chloride, which is NH4Cl. And because I'm heating up my ammonium chloride, this means that my forward reaction is endothermic because it's requiring energy to be put in. And this means my reverse reaction is exothermic. Always in a reversible reaction, it's important to remember if the reverse is endo, the backwards must be exo, or if the forwards is exo, the backward must be endo. Now, if you leave this reverse reaction on long enough and you've got this atmosphere of ammonia and hydrochloric acid and you have the heat down here and it can't escape, what you end up with is what's called a dynamic equilibrium. And what it means to be a dynamic equilibrium is where the forwards and backwards reaction are happening at the same rate. And this leads forward really well in order to explain the next part of the video, where we're going to look at reactions that are in dynamic equilibrium and how to affect the position of my equilibrium in order to create a better yield for my reaction. So here I have two reversible reactions, and what I'm looking to do is use something called Le Chatelier's principle in order to get a better yield for my reaction. So what is Le Chatelier's principle? Le Chatelier's principle is basically that a reaction in equilibrium will counteract change. Now, what do I mean by that? Well, what I mean by that is if you increase the temperature, the reaction is going to try and decrease the temperature. If I increase the concentration of one of my reactants, the reaction is going to try and decrease the concentration of that reactant. Or if I increase the pressure, the reaction is going to try and decrease the pressure. So let's look at these two examples of reversible reactions in equilibrium and look how I can increase the yield to maximize the amount of product I'm making. So here I'm looking to make as much ammonia as possible, NH3. How do I do this? Well, the forwards reaction here is exothermic, meaning the backwards reaction must be endothermic. Now, if I increase the temperature, what's my reaction going to try and do? It's going to try and decrease the temperature of the reaction. And how's it going to do that? It's going to do that by favoring the endothermic reaction. Because remember, endothermic reactions decrease the temperature of the surroundings. So it's going to push my reaction backwards. But if I'm wanting to increase the amount of ammonia I'm making, what I'm going to actually have to do is I'm going to have to decrease the temperature. And if I decrease the temperature, what's my reaction going to do? It's going to shift forwards. It's going to shift my reaction forwards to increase the yield of NH3 because the exothermic reaction will be favored if I do this. So I also said we can do something with pressure in order to increase my yield. Well, let's have a look at how that works. On this side of my reaction, on my reactant side, I have 4 moles of gas. I've got 1 mole of nitrogen and 3 moles of hydrogen, and I'm making 2 moles of NH3. Now, it's important to remember from quantitative chemistry that 1 mole of gas occupies the same volume, 24 decimeters cubed. And if I've got 2 moles on this side and 4 on this side, 2 moles is going to occupy less space. If I increase the pressure, the reaction is going to try and decrease the pressure, and it will do this by by shifting my reaction forwards to make less moles. So if I increase the pressure, we're going to get a shift forwards, and the reason is because there are less moles of NH3, so it occupies less space. There is another thing I can do in order to increase the amount of ammonia that I'm making and shift my reaction forwards, and that is removing the NH3 when you make it. If you remove the ammonia as you make it, what it's going to do is it's going to shift the reaction forwards to try and make more ammonia. You can also do this by adding more N2 and H2 as well. What that's going to do is shift that reaction as far forwards as it can, because it's going to try and remove the nitrogen and hydrogen that you've added and remake the ammonia that we're removing. This reaction below is another really important reaction in chemistry. It's called the contact process, and it's what we use in order to make sulfuric acid. And exactly the same, it's exo in the forward, backwards in the endo, and you're going to need exactly the same things as the first one. But what we're going to do is we're going to look at what this is going to do to my rate of reaction as well, because we've looked at how to increase the yield, but we're going to look at a few compromises you have to make in rate as well when we do this. So if I decrease the temperature, I'm going to increase the yield. But what's that going to do to my rate of reaction? I'm going to increase my yield, I should say, that is of the sulfur trioxide, because that's what I'm trying to make in this reaction. What's that going to do to my rate of reaction? Well, this is going to slow the rate down, because if you use a lower temperature, you're going to get less collisions happening with less energy, so you're going to get less successful collisions. So what they actually do in the contact process is they make a compromise between rate and yield. So they actually use a temperature of around 450 degrees centigrade. And they are also going to increase the pressure. Just have a look at this. To increase the yield, just like the before, it will increase the yield because I've got 3 moles of reactant and 2 moles of product. So if I increase the pressure, it's going to try and decrease it by making the thing that occupies the least space. Now, what they choose for a pressure here is they choose a pressure that is a compromise, again, because creating really high pressures can be dangerous and also can be very expensive to create. So they choose a pressure of around 4 or 5 atmosphere pressure, which isn't very high. I know the above one uses, for the Harbour process up here, that uses 200 atmospheres of pressure. Whereas this one down here actually only uses around 5 atmospheres of pressure. And the reason is, although we'll get a bigger yield, it's expensive and dangerous to create these really high pressures. Now, something they do in order to increase the rate without affecting the yield is they add catalysts. Now, catalysts have no effect on yield. It doesn't affect the equilibrium position. However, it does increase the rate of reaction. Now, that is all for today's video. I hope you enjoyed it. I hope you learned a few things. Please remember, if you did, to drop the vid a like, and please subscribe to the channel.